Alright, we have the function f of x equals cosine of 2x, and our directions to begin with are to write the first four non-zero terms of the Maclaurin series for f of x. So that's the Taylor series centered at x equals 0. So we're going to need values of the derivative. We're going to need to know, of course, what f of 1 is. Excuse me, that's not right. We want to know what f of 0 is, so because our function is centered at 0. And cosine of 0 is 1. We're going to need the first derivative of our function, and that would be negative 2 sine of 2x, and that first derivative is going to be 0. Okay, so the first derivative is involved in the coefficient of the second term. That coefficient is going to be 0. So that's not going to end up counting in one of our first four non-zero terms. Second derivative, negative 4 cosine of 2x. Evaluate that at 0, and you've got negative 4. Third derivative will be 8 times the sine of 2x. Evaluated at 0 would be 0, so that one's not going to count. Going to have to keep going. The fourth derivative would be 16 times the cosine of 2x. That derivative then evaluated at 0 is 16. Fifth derivative. Okay, so wait, I've got 1, 2, 3 terms that are going to have non-zero coefficients. So I need one more non-zero term. So fifth derivative is negative 32 sine of 2x. Evaluated at 0, that is 0. All the ones that are sine are 0, and all the ones that are cosine have some other value. So the sixth derivative would be negative 64 cosine of 2x, and that derivative evaluated at 0 is negative 64. So cosine of 2x is equal to f of 1 plus, okay, we'd have our f prime of x times x is going to be 0. So the next term we need, we're not going to use that one. The next term we need would be the second derivative. So that's going to be a negative 4 divided by 2 factorial times x squared. And then the third derivative is 0. So we're not going to use that term. The fourth derivative evaluated at 0 is 16 over 4 factorial gets multiplied by x to the 4th power. Fifth derivative 0, and then our sixth derivative is negative 64 over 6 factorial x to the 6th power, and that's going to keep going in that same pattern. So simplifying that, we have 1 minus 2x squared plus 2/3 x to the 4th minus 4 over 45 x to the 6th power are the first four non-zero terms of that power series. Then if we needed to write that using the summation notation, that sum, if we started at 0 and go to infinity, since we've got alternating signs, we'll have a negative 1 to the k power, and then that's going to get multiplied by 2x to the 2k power divided by 2k factorial. So we need to be able to write it in that form, and you figure this out by looking I would look at the non-reduced form of that power series. Look at the terms here to come up with what the pattern is. And then, of course, this is the term we have when n is equal to 0. This is what we get when we have n is equal to 1. N, or k, either one. K is equal to 2. K is equal to 3. So these ought to be k's. So you have to have that notation to be able to find the interval of convergence, because we've got a factorial. I'm going to use the ratio test, which is the limit as k approaches infinity of the quantity 2x raised to the 2k plus 2 power divided by the quantity 2k plus 2 factorial. And that's multiplied by the reciprocal of the kth term. So I'm dividing a sub k plus 1 by a sub k. Okay, I'll leave the interim steps to you, because I think you can do that. I end up with, after a step or two, k is approaching infinity, and we've got the quantity 4x squared over 2 times k plus 1 times 2k plus 1. And this is how I'm looking at it. I can reduce the 2 and the 4, and as far as we're concerned right now, x is constant, so we can pull out the absolute value of x squared and just look at a limit as k approaches infinity of 2 over k plus 1 times 2k plus 1. And that limit is going to 0, so we have the absolute value of x squared multiplied by 0, which is going to be less than 1 for all x. So the interval of convergence is all real numbers. Okay, along the same lines, some other examples. If you know a power series for a particular function, so let's say we start with a sine function, we can use that power series to find a power series for functions that kind of come from that. So let's go with the first 4 non-zero terms of each of these. In number 1, the sine of x squared, you're simply going to substitute an x squared in the original power series everywhere there's an x. So we'll have x squared minus x squared cubed over 3 factorial plus x squared to the 5th over 5 factorial minus x, bad looking x squared to the 7th over 7 factorial, which would then simplify to x squared minus x to the 6th over 3 factorial plus x to the 10th over 5 factorial minus x to the 14th over 7 factorial. Okay, the second power series we're looking for is the series for x times sine of x. And you are simply going to take x and multiply it by each of the terms in the original series. So x minus x cubed over 3 factorial plus x to the 5th. Okay, and I should go back to the last example. Indicate that that series doesn't stop. We're just looking at the first 4 terms, but it keeps going forever. Alright, so back to the example at hand. Minus x to the 7th over 7 factorial, and so on. So distribute that x. X squared minus x to the 4th over 3 factorial plus x to the 6th over 5 factorial minus x to the 8th over 7 factorial, and so on. And then of course our third series, the sign of the quantity negative 2x. Be careful with that sign. So we are substituting negative 2x in our original function every place there was an x. To x to the 5th power over 5 factorial, that should be a minus negative 2x to the 7th over 7 factorial, and so on. So cleaning that up, negative 2x plus, think about cubing a negative 2. You're going to get a negative 2 cubed, a negative 8 times a negative is plus. And I'm going to write that as 2 cubed x cubed. You certainly could write that as an 8. But sometimes it's easier when we're trying to recognize patterns to leave it in the power form. Alright, our next term is going to be negative. We'll have 2 to the 5th x to the 5th over 5 factorial. Next term is positive 2 to the 7th x to the 7th over 7 factorial, and so on. So plugging in that negative 2 changes the sign of each of our terms.